we're paying attention, because some things are in fact the same and I might go fast again. But is this next and previous? Okay. So my project this summer was two things, was using SiPM-on tiles to measure the effectiveness of the what? What's that? To measure the SiPM-on-Tile Hadron Calorimeter, which is the same thing that Cameron was talking about. I was in Helen Keynes's group. Dr. Havener was in fact working on PF-Rich, which was the backward coder, which you will also see in this presentation. But the Electron Ion Collider, the eIC, which will be built in 2035, as predicted, because things always go according to plan, aims to study. Oh, the screen just doesn't let the pointer go.
Yeah, the laser pointer doesn't.
That's wonderful. So it aims to study two main things. These, which are called quarks, which are up here in the purple, in the fundamental particles, and the fourth carriers that go between them, called the gluons. Quarks and gluons make up basically everything in the known universe. Inside of every proton, there are 2 ups and 1 down quark, and inside of every neutron, there are 2 downs and 1 up quark. You can make heavier quarks, such as strange, charm, top, and bottom, but you don't really see those in nature very often. You really only get them in collisions. Picture here is the actual schematic for the eIC. Protons or hadrons coming down here in this yellowish circle, and they circle around at almost the speed of light. And the electrons come in from this electron source and go the other way in the blue circle, again, almost at the speed of light. They collide down here at IR6, where the ePIC detector actually is, which is what we actually work on. Picture here is the schematic for the actual ePIC detector. Hadrons come in this way, which we, as physicists, say is the forward direction. And then electrons come the opposite direction, which we say is the backward direction. There are many different detectors all throughout this, but the one we focus on is, in fact, the LFH calorimeter, which is in the forward position. The one that Dr. Havener works on, PF-Rich, is down here in the backward calorimeter. Pictured here is an actual schematic of the LFH cal, or the longitudinally segmented forward hadronic calorimeter. Totally not a mouthful at all. All that really means is that we have arrays of tiles that are separated by massive amounts of steel to be able to slow down particles that are going really, really fast. Here's an array of the actual tiles with a tile that is then wrapped in what's called ESR foil to trap light. It is then placed on an FEB board, which has a silicon photomultiplier on it. And then it is placed between these 2 Kapton foils and placed in a large array like that one right there. It is then slid into this tower and then separated, segmented by steel beams. So here, pictured there are actual diagrams of the tiles. Or not diagrams, but actual pictures of the tiles. Up here is the actual tile, and then down there is it illuminated by the blue light. Here's a schematic of the actual tile with the SiPM sitting in the dimple. What happens is a particle from the collision comes down and hits the tile. It then deposits an amount of energy in the tile, and that energy is converted into a photon. These photons bounce around inside the tile, mainly because of the ESR foil, until they hit the dimple. When they hit the dimple, they cause an avalanche inside of the SiPM, which just means that a whole bunch of electrons get tipped off, very similar to how I'm sorry, I'm blanking on the name. A light battery works, how we get energy from light. Yes. So pictured here is the actual silicon photomultiplier on an FEB board. The actual silicon photomultiplier is incredibly tiny, and if you hold it under a microscope, it is quite brilliantly designed. But unfortunately, you can't actually see that here. But it sits here on the FEB board, which contains lots of wiring and stuff so that we can actually read the signals that come out of it. To test it, we hung an LED source, pictured up here, which fires a blue wavelength light at the silicon photomultiplier. It then hits it very consistently, and we were able to read that data and send it off to a kind digitizer. We use a Faraday cage in this setup, which acts as a dark box, blocking outside photons and outside light from actually getting in. Otherwise, it would cause what's known as a voltage drop. Yes, inside the SiPM, and would cause an error. So what actually happens when we read the data from the SiPM is that the data is sent to our kind digitizer. The digitizer then splits the data off after every hit into what is called a high and low gain, which are just terms for analog to digital conversions in this case. The high and low gain data should only be differing by a scale factor, and because of that, we expect them to be linearly correlated. However, when we took test beam data from CERN for our early designs, they weren't linearly correlated. So we need to figure out why. So this entire project was focused on trying to replicate that CERN test beam data. Pictured here is the actual histogram of the high and low gain, with the low gain in blue and the high gain in red. Low gain is better for high energy signals like hadronic showers, stuff that's easier for us to read and is much harder to saturate. At high gain, it's much easier to see things that are like very low energy individual photon peaks, possibly minimum ionizing particles, and we can see larger swaths of data. However, high gain has a much higher likelihood of becoming saturated because we amplify it so much. We can only hold up to 8,000 channels. So the first test that we did was we tested cosmic data. Cosmic data is a very well-known test that happens all the time with these kinds of scintillating tiles and SiPMs. What we do is we arrange 3 SiPM-on tiles of similar make, and we hook them to different channels. We then use logic to determine if a particle manages to hit the edge of a tile or pass through all 3 tiles. We only read it if it passes through all 3 tiles because we want a consistent readout. With that, we were able to get 3 graphs from each channel, and we were able to plot each one with a linear slope. And as you can see, these slopes were incredibly similar, well within our working parameters to be able to say that our SiPMs do in fact have a linear correlation. Between 9 and 10 was what we were aiming for and what we were expecting to see for the rest of our time. So our next run was using the actual LED. What we did was we simply shone the LED on it at different voltages of the LED, at different wavelengths, and at different trailing edges to be able to see if we could replicate some sort of non-linearity. The first thing that we immediately noticed was that the pedestal was getting in the way. The pedestal is this like arbitrary unit that just happens to be in the kind digitizer. It gets in the way of a lot of things. So we ended up putting a function onto it and stating that anything that fell below it, anything in yellow here, we throw out and we don't fit. That immediately fixed a lot of slope issues. And we started getting much more consistent slopes, such as 9.72. And then pictured here is the lower voltages around 3.110. And then pictured up here are the higher voltages at 3.18. We typically range from 0.1 voltage between each LED run. So pictured here is the actual histogram of slopes. As you can see, they're like really, really similar between 9.65 and 9.85 of each other, with such a similar difference between them across 0.8 voltages as we used here. We didn't really replicate test beam data here. So we figured the SiPMs were in fact working as we expected them to. So maybe we need to move on to something else. Our next idea was that using multiple SiPM-on tiles together were in fact causing a pull of voltage away from one tile and feeding it to another. If tiles don't have enough voltage applied to them, then they can not read out as much data as we need them to. So what we did is we linked 3 tiles together in a daisy chain. We then only read one at a time with disconnecting the other 2. What this did was enable us to see very clearly if one was incredibly different from the other when they were daisy chained versus individual. And while you can't see the slopes pictured here because they were incredibly small writing, they were incredibly similar to the point that you couldn't even tell the graphs apart if you held them side by side. So that was also not replicable with test beam data. Our final idea, and the most promising idea, was to pulse the LED at different wavelengths and see if that was in fact something that could replicate test beam data. As you can see here, we applied a Cole-Z plot to check saturation of points, which were highly saturated near the 0 mark. And we tried to apply a linear fit to it, but it doesn't exactly look very linear. This looks very banana-shaped. For lack of better terms, the experts in the field got extremely excited when they saw this, because that was not linear. So this looks very similar to test beam data, and while conclusions have not been finalized, further tests are currently ongoing to see if frequency was in fact something that could have caused the SiPMs to quote unquote break in the test beam data. My next experiment was exactly what Cameron was talking about. We had to measure the dimensions of the scintillating tiles. Picture here is the setup that I actually used, so graciously given to me by Cameron. But briefly, as Cameron already said, we pick up tiles from this input bin, we carry them over to this camera, take a picture of them as they're illuminated by this black light, and then put them back in this output bin. We are then able to get images that look like this, and we extract them going all the way down to be able to get two images like this, with one being the length of a tile this way in pixels and one being the width of a tile this way in pixels. Tiles are supposed to be uniform, 5 by 5 centimeters, but they almost always have a longer and a shorter side, typically around 4.8 millimeters and 4.75 millimeters. The first thing that I had to do to be able to actually use this new setup was to recode the graphical user interface, or the GUI, that was left behind by another student named Grant Phills, who was incredible and managed to code this entire thing from scratch. But unfortunately, this was not very user-friendly, and it didn't work with the 200 tile scan that we had. So I modified it, and I made stuff very easy to use. When you hit the 200 tile scan button, a new window pops up with a schematic of the input bin, in which you can input exactly how many tiles are in each bin. Let's say you don't have 200 tiles. Let's say you have 199, which was in fact a problem we had. And you realize that you can't put 25 in bin A. Excuse you. So you put 24. The code accounts for that, and it runs with only 24 in the bin. Once you're done with that, you still need a way to be able to extract it. Previously, you had to manually go into VS Code and find the extraction code and put in the file name. Now, you just hit graphing extraction. It pulls up the graphing window. And while it's not here because it didn't actually fit in this image, there is another extracting option that comes up, and you click, I would like to extract the most recent run. And you click extract, and it extracts it, the entire thing by hand, by each image very, very quickly. Okay. Ooh, okay. And then also in this slide that you can see is the graphing option, which right after extracting, you can just hit, I would like to graph the same run, and you have many options to graph, including scatter plots of the sides, individual histograms to tell you exactly what we thought each side was, and scatter plots of the dimple sizes. Picture here is an actual graph we got for a test run for 20 molded tiles, which were very good because they all are always very, very consistent in size, whereas machine tiles are man-made, so they're much likely to not be consistent in size. Excuse me. As you can tell by our data, we were incredibly close, within like 100 microns of each other. And while we do have a little bit on an offset, we ended up accounting for that with our multiple runs, because some were higher and some were lower, but they were always within 100 microns of each other. So because of this, we were confident enough to be able to move on to machine tiles, the ones that we actually need to measure, because they're more likely to differ in length. The other thing that we were able to do was to measure the actual thickness of the tile based on the dimple diameter. If tiles are too thick, then they have differing light yields, and if tiles are too thin, they might have not enough light yield. Most of the tiles tended to be around 4 millimeters in thickness, but some could be smaller, some could be higher, depending on how the amount that the diamond ball drill that was used to cut them went down. The thicker the tile, the more the diamond ball drill went down. The thinner the tile, the less the diamond ball drill went down. Tiles too thick also won't actually fit inside the calorimeter because they'll push against the steel that they're next to, the Kaplan foil. So in conclusion, we had two different projects this summer. One was testing silicon photomultipliers, in which we tested and coded the analysis of multiple different methods, including cosmics, LED runs, daisy chained, and high differing frequencies. The differing frequencies was most likely to be an issue, as it was the most close to replicating the test beam data, but we weren't able to perfectly replicate the test beam data. To which I acknowledge some further undergrad who will probably be taking this up. In the tiles, we were able to modify and create a new code for pixel milliliter conversion, and we were able to actually run 200 tile. Almost done. We were able to actually run 200 tiles fully automated. We were able to make a graphical user interface that was much more accommodating, and we were able to take accurate measurements within 100 microns of tiles. and we're able to accurately implement a method of discerning a tile thickness via their dimple. With that, I'd like to acknowledge the national labs listed here, as well as the STAR summer program, who made me present this 4 times this week. The Yale College Dean's Office for their gracious money, because I love money. And in Wright Laboratory, Helen Keynes and Prakar, because quite frankly, I love it when people tell me I'm wrong, because I am wrong quite often, and they were not afraid to tell me that I was in fact very, very wrong a lot of the time. But really, thank everyone in Keynes's lab group for making this one of the best summers of my life. And that is my presentation.
Oh, hi Nathan, very
Hi.
nice. Hi. Very nice talk. Can you go back to slide 14?
Yes. Also, you love that my slides are in fact numbered. Stars did not want me to have my slides numbered, but Helen was
Why?
like, yes, numbered slides.
Okay. So I'm not fully
Yes.
grasping the test beam setup that you're trying to replicate. What about these different frequencies are you trying to replicate? Because do you know like what equivalent frequency the test beam would be at?
So that is a good question. I do not know what frequency the test beam data was run at. I think this test was more to just see if they do vary in frequency at all. Because as I'm assuming, I'm not actually there at the test beam, I'm assuming frequencies can vary quite a bit. So higher frequencies, lower frequencies, depending on what kind of collision happens. I think the goal of this was just to see if running at differing frequencies can have a difference, and whether or not that could actually impact the data we get.
All right, thank you.
Hi, I was just wondering the scale of the EIC.
In what regard?
How big is it? I didn't catch any sort of, I don't need exact measurements necessarily.
So there's another collider already on Brookhaven National Laboratory called RIG. The EIC is supposed to be built on top of RIG. So I toured there, it was very, very big, as I assure you. It takes up almost the entirety of the island, but I don't know the actual dimension.
It does not take up the entire island.
Does it?
It does not.
I thought it was a smaller island that it sat on, and the whole island was over there. I stand corrected. As you can tell, Kansas Lab group corrects me all the time. It's great.
The ring is like a couple of miles in circumference, and the detectors, ePIC will be like, you could fit 3 school buses in it. That's about how big it is.
And we will be doing.
Oh yeah.
Yes, Emily?
Yeah, so question about the pedestal, which hopefully this isn't a mean question. I don't know how much you actually were looking at.
That's the best way to start.
Shaking now.
But it looks like from the yellow, the pedestal was set pretty high to
Yes.
like 200. I'm assuming, were you just using the same pedestal that was set at the test beam?
That is a great question. So in the Kind digitizer, there are 2 main pedestals that we used. There is, if you run it at 8K spectroscopy, which means you have 8,000 channels, which typically has like higher grain and higher like precision. You have a pedestal of 50. When you run it at 4K spectroscopy, you have a pedestal of 25, double. The function that we use to be able to cut off the pedestal is we use a function that is, in fact, I actually have the histogram on here. Thank you, Helen, for telling me to have an appendix. Right there. So this was 4K, that was 8K. What we do is we make a histogram and it tells you, what the actual pedestal was. But what you do is you make a function that is, okay, here's the mean of the pedestal, here's the width of the pedestal. What we do is we do the mean of the pedestal plus the width, and then you multiply that by 5. So you get roughly 200 for I think it was 250 for, no, it was 200 for 8K and about 150 for 4K, I believe. And then you just cut everything off below that. That was given to us by Frederica in BNL.